Why can Wi-Fi go through walls while light cannot? I want to go straight into this question right from the start, because if you truly understand it, you will realize that the world around you is not as simple as you think. Let's start with an important truth. The Wi-Fi signal from the router in your house and the light from the lamp in your kitchen are actually the same physical phenomenon. They are both electromagnetic waves. This is not speculation, but was proven in 1865 by James Clerk Maxwell, who wrote the equations describing how electric and magnetic fields propagate through space. And from that showed that light is a form of electromagnetic wave. Now let's look at the specific numbers so you can see it more clearly. Wi-Fi in your house typically operates at frequencies around 2.4 gigahertz or 5 gigahertz, which is a few billion oscillations per second, while visible light has much higher frequencies in the range from 4 times 10 Mach or Hz to 7.5 times 10 Mach or hertz, which is hundreds of trillions of oscillations per second. But despite the difference in frequency, both obey the same Maxwell's laws and both travel at the speed of light, about 3 times 10^8 meters per second. Now put yourself in a very familiar situation. You are in a typical house in the United States. The Wi-Fi router is in the living room, and you walk with your phone to the bedroom, passing through a dry wall about 1-2 centimeters thick, or even upstairs through wooden floors and ceilings, and the signal still works. It may weaken a bit, but clearly it has gone through the walls without any major problem. You take this for granted because it happens every day. But now try something different. Turn on the light in the room, then step into the next room and close the door. The light almost completely disappears. The wall blocks it absolutely. You don't see light going through the wall. Not even a tiny ray slips through for you to notice. And this is exactly the strange point I want you to think about. We are talking about the same type of wave, the same physics, the same laws, but one goes through walls almost without obstacle while the other is completely blocked. This is not just a small detail. It is a direct contradiction to the way you have understood the world since you were a child. So the question is, if electromagnetic waves are one and the same, why do they behave so differently? And the deeper, more interesting question is, are the waves themselves different, or have we misunderstood how matter the walls around you actually works? If you are like most people, you will quickly come up with a very reasonable sounding explanation for this paradox. Wi-Fi has a long wavelength so it can slip through the gaps in the wall, while light has a very small wavelength so it hits the matter and gets blocked. Sound familiar? In fact, this is the most common explanation I have ever heard, even from very confident physics students. And to be fair, the idea sounds reasonable at an intuitive level, because in everyday life, bigger things usually get past obstacles more easily than smaller ones. Let's put some specific numbers on the table to see if this intuition really holds up. Wi-Fi operates at about 2.4 gigahertz, corresponding to a wavelength of about 12.5 centimeters, which is roughly the length of a pencil. Visible light, on the other hand, has a wavelength of only about 400 to 700 nanometers, which is 4 times 10^10 meters, which is 4 times 10^10 meters, hundreds of thousands of times smaller than Wi-Fi. So the story people tell themselves is, long waves like Wi-Fi are big, so they can bend around obstacles or go through gaps, while light is small, so it gets stuck when it hits matter. But this is where everything starts to fall apart if you look a little closer. You see, if you want to talk about gaps, then you have to know the actual size of those gaps. In a solid material like drywall, wood, or brick, the distance between atoms is only about 0.1 nanometers, or 1 angstrom, which is 10 ast-hana-meter, which. This is an extremely small number. Now compare this number with light. Visible light has a wavelength of about 500 nanometers, meaning it is about 5,000 times larger than the distance between atoms. If you really believe in the slip-through-the-gap model, then light should not only go through the wall, but it should do so extremely easily. Because from light's perspective, the atoms in the wall barely exist. They are way too small compared to its wavelength. By that logic, the wall should look like a sparse net to light, almost completely transparent. But in reality, it is the complete opposite. Light is blocked almost completely. You don't see light from the next room coming through the wall, not a single sign that it can slip through the gaps. So right here, the size theory has run into a serious problem. Not a small error, but a complete contradiction with reality. And if you think this is just a small detail that can be fixed, let me make things even worse for that theory. Let's talk about X-rays. In 1895, Wilhelm Röntgen discovered a new type of radiation that he called X-ray. These rays have wavelengths in the range from 0.01 to 10 nanometers, which is tens to hundreds of times smaller than visible light. According to the size logic, X-rays should be blocked even more easily than light, because they are smaller and would get stuck in the atomic structure more easily. But what actually happens? X-rays go through your body, through skin, through muscle, and are only strongly absorbed when they hit denser materials like bone or metal. This is why X-rays are widely used in modern medicine for X-ray imaging, allowing doctors to see inside the body without surgery. Now you have a very strange situation. Radio waves with long wavelengths go through walls. X-rays with extremely short wavelengths also go through matter, but visible light, which sits in the middle of the two, gets blocked. If you draw a spectrum from radio waves to X-rays, you will see that there is no simple rule like the bigger it is, the more it penetrates, or the smaller it is, the more it gets blocked. In reality, both ends of the spectrum penetrate well, while the middle part gets blocked. This completely breaks the size-based story. And if you still want to save that theory, think one step further. If everything is just a matter of size, then materials with similar atomic structures should behave the same toward light. But they do not. And we will see that clearly in the next part. So at this point, I want you to do what science always demands. When an idea does not fit the experiment, you have to abandon it. The size theory sounds reasonable, but it does not explain light. It does not explain X-rays, and it does not match any of the experimental data we have. And in physics, that is the clearest sign that we need a completely different understanding. Now let's look at a series of very simple but extremely uncomfortable examples for the idea that everything is just a matter of size or gaps. Let's start with two familiar materials, wood and glass. Both are solids, both are made of atoms packed tightly with average distances around 0.1 nanometers. And at a coarse level, their structures are not hollow in the way intuition usually imagines. If you keep the chicken wire model in your head, then these two materials should behave almost the same with light, because the gaps between their atoms are not significantly different. But in reality, it is the complete opposite. A transparent glass pane made from silica, can transmit up to about 90% of visible light under ideal conditions. That is why you can look through a window without any significant obstacle. Meanwhile, a wooden board just a few centimeters thick will block almost all light, so you cannot see through it even a little. Two materials, both solids, similar atomic spacing, but completely different behavior with light. This cannot be explained by size alone. The deeper reason lies in the electronic structure. Wood is a complex organic material made of cellulose, lignin, and many large molecules with diverse chemical bonds. These structures contain electrons that absorb the energy of visible light very efficiently, causing the light to be held back, turned into heat, or scattered in many different directions. In contrast, silica glass has an amorphous network structure in which the electrons are bound in a way that they do not easily absorb the energy of photons in the visible light range. So, light can pass through without being blocked. Now let's move to a completely different material, water. Water is a liquid. Its molecules are not stationary but are always moving, sliding past each other and changing position continuously. The average distance between water molecules is about 0.3 nanometers, larger than the distance between atoms and many solids. If you still hold on to the thinking based on gaps, then water should block light less or at least behave very differently from solids. And in reality, water is transparent to visible light. You can look through a glass of water, look down to the bottom of a lake, or see fish swimming underwater without any major obstacle. But the important thing here is, the same logic does not explain why wood, with atomic spacing similar to glass, is not transparent. To make it clearer, Let's consider a familiar quantity in optics, the refractive index. The refractive index of water is about 1.33, and that of glass is about 1.5. These numbers tell how light is slowed down and bent when passing through the material, reflecting how the electrons in the material interact with the electromagnetic field of the light wave. But what is noteworthy is that both water and glass let light through, even though their structures are very different, while wood does not. If everything depended only on geometry or gap size, then we could not explain why these three materials give three different results. And things get even more complicated when you look at other materials. Metals reflect almost all light, while some types of plastic are transparent. There is no simple rule based on gaps or size that can cover all these behaviors. So what we are forced to accept at this point is the geometric structure of the material. That is, the distance between atoms or its hollowness is not the deciding factor in whether light can pass through or not. That means our entire initial explanation has been heading in the wrong direction from the very beginning. And this is the important moment in science. When an idea that seems reasonable fails in the face of reality, we do not try to patch it up. We have to find a completely new way of looking at it. At this point, I want you to pause for a moment and look back at everything we have just gone through, because if you have truly followed every step, you will realize that something very fundamental in the way you understand the world has started to collapse. We started with an idea that seemed obvious. Big waves go through, small waves get blocked. Sounds reasonable, right? But then we looked at the numbers and everything started to shift. Light has a wavelength of about 500 nanometers, while the distance between atoms in a wall is only about 0.1 nanometers, meaning it is thousands of times smaller than light. By intuition, light should pass through a structure whose holes are much smaller than it. But in reality, it is completely blocked. Then we looked at X-rays, discovered in 1895 by Wilhelm Röntgen, which have wavelengths much smaller than light, and by the same logic they should be blocked more easily. But instead they pass through your body with almost no obstacle. Then we compared materials. Wood blocks light. Glass lets up to about 90% of light through. Water is also transparent, even though it is a liquid with a looser molecular structure. No simple story based on size or gaps can explain all of this at the same time. And when you see an idea fail in so many different ways, that is not a sign that it needs tweaking. It is a sign that it is wrong at the root. This leads us to a very interesting point, and also a bit uncomfortable. Your intuition about matter is wrong. You have been taught since you were little that a wall is something solid, hard, impenetrable, and light is blocked because it hits that wall. But modern physics, especially after Ernest Rutherford's experiments in 1911, shows us a completely different picture. Atoms are not solid blocks, but an extremely small nucleus, about 10 meters in size, surrounded by electrons moving at distances of about 10 meters. That means most of the volume of matter is actually empty space. If you scale an atom up to the size of a stadium, the nucleus is like a speck of dust in the middle. The electrons are somewhere very far away, and the rest is almost completely empty. So why does something that is mostly empty space block light so effectively? And why does the same structure allow Wi-Fi to pass through with almost no obstacle? This is where your classical intuition starts to become useless, because that intuition was built from experience at the human scale, where everything looks solid and continuous, but at the atomic scale, everything works according to completely different rules. And now we have to face a question that I think is the most important in this whole story. If it is not size, not gaps, then what really determines whether an electromagnetic wave gets blocked or transmitted? What is telling light that it has to stop while allowing Wi-Fi to pass? And this is the moment when I want you to feel a little uncertain, a little disoriented, because that is exactly the state science often brings us to before we find the answer. When you step into the world of quantum mechanics, the world built by names like Niels Bohr or Erwin Schrödinger, you are forced to abandon simple visualizations of matter and waves. You can no longer think of light as little balls hitting a solid wall, or of matter as a net with fixed holes. Those images are too simple to describe what is really happening. And the interesting thing is, when you accept that your intuition is no longer reliable in this context, you begin to open up the possibility of understanding something much deeper. That the way electromagnetic waves interact with matter does not depend on size or simple geometry, but on something completely different, something more subtle, more precise, and also more beautiful in terms of physics. But to see that, you will have to be willing to leave behind what you thought you understood and accept stepping into a new way of looking at things, where the answer does not lie in the shape of the wall, but in the nature of what makes it up. So at this point, instead of continuing to try to fix an idea that was wrong from the root, I want you to do something more important. Change the question. Because in science, very often the problem is not that you answered wrong, but that you are asking the wrong question from the beginning. We asked, does the wave slip through the gaps or not? But clearly that question does not take us anywhere. It does not explain light. It does not explain X-rays. And it does not explain the difference between wood, glass, and water. So let's try a different question. A question that I think is more correct. What really happens when an electromagnetic wave meets matter? More specifically, what happens when an electromagnetic wave interacts with electrons inside the material? Because if you look at the structure of matter we just talked about, you will see that everything that can react with electromagnetic waves is really the electrons. The nucleus hardly participates in this story at the energy levels we are talking about, while the electrons carry electric charge, and electromagnetic waves are oscillations of electric and magnetic fields, so they can act directly on electrons. This is the important turning point. We no longer think of waves as things hitting a hard wall, but start thinking of them as energy oscillations acting on electrons bound in matter. And right here, modern physics comes in, especially the developments after 1900, when Max Planck introduced the idea that energy is not continuous but quantized. And then Albert Einstein proved that light is not only a wave, but can also be viewed as separate packets of energy that we call photons. This completely changes the way we understand the interaction between light and matter. Before that, in classical physics, people thought energy could be transmitted continuously, like water flowing from one place to another. But in the quantum world, energy comes in specific quanta that cannot be divided arbitrarily, and this leads to a very important consequence. Electrons and atoms cannot absorb energy arbitrarily. They are not like a ball that can receive any amount of energy and stop moving. Instead, they can only exist at certain energy levels and can only move from one level to another if they receive exactly the right amount of energy needed. This is an idea that was developed further by Niels Bohr and then described more precisely by Erwin Schrödinger's wave mechanics. So now when an electromagnetic wave enters a material, the question is no longer, does it slip through the gaps, but does the energy it carries match the energy levels of the electrons in that material? And this is where everything starts to get interesting, because if the energy of the wave, or more precisely, the energy of the photons that make up that wave, does not match any of the energy levels that the electrons can transition to, then the electrons simply cannot absorb that energy. There is no way for them to receive that energy. Like you cannot climb a step if the distance between two steps does not match your stride. And if the electrons do not absorb the energy, then the wave is not held back. It continues through the material. Conversely, if the energy of the photon matches the gap between two energy levels of the electron, then the electron can absorb that photon, move to a higher energy level, and the energy of the wave is held in the material. This is the basic mechanism we have been looking for, and it has nothing to do with size or gaps. It is entirely a matter of energy matching. And the important thing is, you cannot understand this with classical intuition, because in the classical world, energy is continuous, while in the quantum world it is discrete. So when you shift from the question, does the wave get through, to the question, how do the electrons react to the wave's energy, you are not just changing the explanation. You are stepping into a completely new way of looking at the world. A way where the answer does not lie in the shape of matter, but in the energy structure deep inside it. To understand why electrons play the central role in this story, we need to look back at something that at first sounds familiar, but is actually completely contrary to intuition. Atoms are not solid blocks. When you touch a wall and feel it is hard, you tend to think that inside it is something solid, continuous, and impenetrable. But modern physics shows that is not true. An atom has a structure consisting of an extremely small nucleus at the center, with a size of about 10 meters, and electrons moving around it at distances on the order of 10 meters. This means the atomic radius is about 100,000 times larger than the size of the nucleus. If you imagine scaling an atom up to the size of a stadium, the nucleus is like a tiny speck of dust sitting in the middle of the field. The electrons are somewhere near the edge, and the rest is almost completely empty. This is not just a purely visual analogy, but an experimental result confirmed from the early 20th century. In 1911, Ernest Rutherford performed the famous gold foil scattering experiment. He fired alpha particles at an extremely thin gold leaf and observed how they were deflected. If the atom were a solid block, the alpha particles would have been stopped or deflected a lot. But what Rutherford observed was that most of the alpha particles passed straight through the gold leaf without being affected, and only a very small number were deflected strongly or bounced back. From that, he concluded that most of the volume of the atom is empty space, and the entire mass is concentrated in a very small region at the center, that is, the nucleus. This is one of those moments when physics forces us to completely abandon classical intuition. But if atoms are mostly empty space, then why does matter feel solid? Why can't you push your hand through a table or through a wall if inside them is mostly empty space? The answer lies in the electromagnetic forces between the electrons. Electrons carry negative charge and they obey the laws of quantum mechanics, including the Pauli exclusion principle, which prevents electrons from occupying the same energy state. When you try to push two objects close together, the electrons in them start interacting strongly, creating a very large repulsive force. It is this repulsive force that creates the feeling of hardness that you perceive. In other words, matter is not hard because it is solid, but because the electrons do not allow you to pass through it. This leads us to a very important point in the story. When an electromagnetic wave like light or Wi-Fi enters matter, it does not slam into a solid wall in the classical sense. Instead, it interacts with the electrons distributed in that space. Nucleus hardly participates in this process at all, because its size is too small and the energy required to interact with the nucleus is much higher than the energy of light or Wi-Fi. So everything important happens at the electron level. This completely changes the way you should think about the original problem. Instead of imagining a wave trying to slip through the gaps between atoms, you should imagine an electromagnetic field propagating through a cloud of electrons, where each electron may or may not react depending on the energy of the wave. And it is that reaction, not size, not geometry, that determines whether the wave gets blocked or transmitted. This is an extremely important shift, because it takes us out of the world of simple images and into a much more accurate picture, where matter is no longer solid blocks but dynamic systems of electrons that can interact with energy according to very specific rules. And once you accept this picture, the original question about Wi-Fi and light is no longer a paradox, but becomes a problem that can be explained. Once you have accepted that all important interactions happen at the electron level, the next step is to understand something even more important. These electrons are not free at all the way you might imagine. In the atom, electrons are held in place by the Coulomb force, that is, the attractive force between the negative charge of the electron, number 0.6 times 10, 1.6 times none, 1 Coulomb, and the positive charge of the nucleus, a force described precisely by Coulomb's law from the 18th century. This force is so strong that it keeps the electrons in very specific regions of space around the nucleus, at typical distances on the order of 10 meters. But what is really interesting is not just that the electrons are held in place, but the way they exist and react to energy. If you approach this problem with classical intuition, you might think of the electron like a little planet orbiting the sun. And if you supply energy, it can absorb any amount and change its orbit continuously. But modern physics shows that is completely wrong. Electrons cannot receive energy arbitrarily. They can only exist at certain discrete energy levels, and can only transition from one level to another when they receive exactly a specific amount of energy. This idea was first clearly put forward in 1913 by Niels Bohr when he studied the hydrogen atom and realized that electrons can only exist at certain definite energy levels. For example, 13.6 eV for the ground state, and when moving to a higher level, it must absorb exactly the energy corresponding to the difference between those two levels. Then in 1926, Erwin Schrödinger developed the wave equation that describes the electron as a wave state, and the result remains the same. The energy of the electron is discrete, not continuous. This means the electron is not a flexible system that can react to any stimulus, but a system with very strict rules of the game. Imagine you are standing in front of a staircase where the steps are exactly 1 meter apart. You cannot stand at a height of 0.5 meters or 1.3 meters. You can only stand at 0, 1, 2 meters, and so on. If you want to step to the next level, you must have enough energy to lift your body exactly 1 meter. If you only have enough energy to lift 0.5 meters, you will not go anywhere. And if you have energy to jump 2 meters, you will skip a step and go straight to the higher one. Electrons work in a similar way, but with energy instead of height. For example, in the hydrogen atom, the difference between energy levels can be a few electron volts, eV. And for the electron to transition, it must receive exactly that amount of energy. No more and no less. This leads to an extremely important consequence that I want you to remember. Electrons only react when the energy matches exactly. There is no such thing as close enough. There is no almost sufficient is okay. In the quantum world, if the energy is not exact, the electron simply does not react. It does not absorb the energy, does not change state, and to the electromagnetic wave, it almost does not exist. This is completely different from the way we think in classical physics, where a system can absorb energy gradually and react continuously. Here, everything is discrete, step by step, very precise. And this is the key to understanding our story. When an electromagnetic wave enters matter, it carries energy in the form of photons. If the energy of the photon, calculated by the formula E equals hf with h, 6.6 times 10 for 110 then the electron will not absorb it. The wave will pass through. But if that energy matches exactly, the electron will absorb the photon, move to a higher energy state, and the energy of the wave is held back in the material. This is an all-or-nothing mechanism, and it explains why different types of waves can behave very differently when they encounter the same matter. So in the end, the question is no longer whether the wave is small enough to slip through, but whether its energy speaks the right language to the electron. Now we can go deeper into the most important idea of this entire story, an idea that if you grasp it, everything will become clear. Electrons do not exist in a continuous energy range, but only at discrete energy levels, like steps on a staircase placed at fixed intervals. This is not a vague hypothesis, but a conclusion confirmed by experiment more than a century ago. If you imagine a classical system, like a ball rolling on the ground, you can supply any amount of energy to it, and it will respond correspondingly in a continuous way. But in the atomic world, things do not work that way. Electrons can only exist at certain definite energy levels. For example, in the hydrogen atom, the ground state is 13.6 electron volts eV, and higher levels are 3.4 eV, 1.51 eV, d Bohr 0.51 eV, d Bohr 0.51 eV, and so on according to a specific rule. You cannot find an electron at 10 alaf 10 alaf 10 eV or 5 eV, because those levels simply do not exist in the system. To help you visualize, go back to the energy staircase image. Imagine a staircase with steps spaced at irregular intervals, some high, some low, but each step is a valid position where you can stand. You cannot hover between two steps, and you cannot choose any random position. You are limited by the structure of the staircase. Electrons are the same. They are bound by the energy structure of the atom and can only exist at those specific steps. This leads to an extremely important consequence. For an electron to transition from one energy level to another, it must receive exactly the amount of energy equal to the gap between those two steps. No more, no less. If you supply less, the electron will not move. If you supply more, The electron cannot stop halfway. It can only make precise jumps. This is the very nature of discreteness in quantum mechanics. And the interesting thing is that this idea did not just appear in theory, but was observed very early in the history of physics. In the 19th century, scientists studying light emitted from atoms discovered that it does not produce a continuous spectrum, but a set of distinct bright lines at very specific wavelengths. This is called the line spectrum. One of the most famous examples is the spectrum of the hydrogen atom, studied by Johann Balmer in 1885. He noticed that the bright lines in the hydrogen spectrum follow a very precise mathematical formula related to wavelengths such as 656 nanometers, 486 nanometers, 434 nanometers, and 434 nanometers. These numbers are not random. They correspond exactly to the energy levels between which the electron can transition. When an electron in the hydrogen atom falls from a higher energy level to a lower one, it emits a photon with energy exactly equal to the difference between those two levels. And this photon has a specific wavelength that we observe in the line spectrum. This is direct evidence that the energy of the electron is not continuous but quantized. And what is even more important is if electrons can only absorb or emit energy at very specific levels, then that also means they can only interact with electromagnetic waves when the energy of that wave matches these levels. This is the bridge between what we have said about electrons and the original question about Wi-Fi and light. Because if a photon has energy that does not match any energy gap between the levels of the electron, then the electron cannot absorb it. And if there is no absorption, then there is no absorption. Then there is no blocking. The wave will continue to pass through. But if the energy of the photon matches exactly a gap between two levels, the electron will absorb that photon immediately, move to a higher energy level, and the energy of the wave is held back in the material. This is an extremely strict rule with no exceptions. And when you have seen that electrons only exist at discrete energy levels, the next step is to understand exactly what energy an electromagnetic wave carries, because this is the missing piece that connects everything together. In 1900, Max Planck put forward an idea that sounded very strange at the time. Energy is not exchanged continuously, but in small packets that he called quanta. He was trying to explain blackbody radiation, a big problem in physics at the time. And to do so, he was forced to assume that the energy of light could not have any arbitrary value, but could only exist at discrete levels proportional to its frequency. At first, even Planck saw this as more of a mathematical trick than a physical truth. But just a few years later, in 1905, Albert Einstein took an important further step when he used this idea to explain the photoelectric effect. In this experiment, light shining on a metal surface can knock electrons out of that surface. But the surprising thing is that this only happens when the light has a high enough frequency, no matter how strong its intensity is. Low frequency light, no matter how intense, cannot free electrons, while high frequency light, even if weak, can. This completely contradicted classical physics, where people thought energy depended on the intensity of the wave. Einstein explained that light is not only a wave, but also consists of separate energy particles called photons, and each photon carries a definite amount of energy. The formula describing this is very simple, but extremely profound. E equals hf, where E is the energy of one photon, f is the frequency of the wave, and h is Planck's constant with a value of about 6.626 times 10 or Joule second. This means the energy of a photon is directly proportional to frequency. The higher the frequency, the greater the energy. Let's put a few numbers in so you can see it more clearly. A red light photon with a frequency of about 4 times 10 hertz has an energy of about 1.6 electron volts eV, while a green light photon with a frequency of about 6 times 10 hertz has an energy of about 2.5 eV. Violet light with an even higher frequency can reach about 3 eV. Meanwhile, a Wi-Fi photon at 2.4 gigahertz, that is 2.4 times 10 stinthundredths, has only about 10 stinthundredths eV, which is about 100,000 times lower than visible light. And if you go up to higher energies, like X-rays with frequencies around 10 hertz, each photon can carry energies of thousands of electron volts, that is keV, enough to penetrate body tissue and even ionize atoms. These numbers are not just technical details. They are the key to the entire problem. Because when you combine the formula E equals hf with the idea that electrons can only absorb energy at certain definite levels, you begin to see a clear picture. Each type of electromagnetic wave carries different packets of energy, and only those packets of energy that match the energy levels of the electrons can be absorbed. This explains why frequency, not size or intensity, is the deciding factor. In the photoelectric effect, low-frequency light does not have enough energy to knock electrons out of the metal, no matter how much you increase the intensity. But high-frequency light can, because each photon carries the necessary energy. And this is exactly the principle we will apply to the original question. When an electromagnetic wave enters matter, what matters is not whether it is big or small, but whether the energy of each photon in that wave matches the energy levels of the electrons. If you understand this, you already have in your hands the tool to explain why Wi-Fi can go through walls, while light cannot, and why X-rays can go through the body. It all comes back to the same simple but powerful principle. The energy of the photon, determined by its frequency, decides how it interacts with matter. Now we can put all the pieces together to see the real mechanism that takes place when an electromagnetic wave meets matter, because at this point you have all the tools to understand it. Imagine a photon, a packet of energy we just talked about, entering a material. This photon carries a definite energy given by the formula E equals hf, and that energy cannot change continuously. On the other side, you have the electrons in the material. These electrons can only exist at discrete energy levels. For example, 13.6 eV, 3.4 eV, or other levels depending on the atomic and molecular structure. Now the only question is, does the energy of the photon match the gap between two energy levels that the electron can transition to? If the answer is yes, then something very specific happens. The electron will absorb that photon, receive all of its energy, and jump from a lower energy level to a higher one. The photon disappears. The energy of the wave is held back in the material, and from your perspective, the wave has been blocked. But if the answer is no, if the energy of the photon does not match any gap between the energy levels of the electron, then the electron has no way to absorb it. It cannot take a part of the energy, because in the quantum world there is no such thing as splitting a photon. Either the electron absorbs the whole photon or nothing happens. And if nothing happens, the photon continues moving, passing through the material as if the material did not exist. This is an extremely strict law, and it has been confirmed through countless experiments in optics and atomic physics for more than a century. From the absorption spectra of atoms, high-precision spectroscopy experiments, to practical applications like lasers, everything is based on this same principle. Absorption only occurs when the energy matches exactly. For example, in spectroscopy experiments, you shine light through a gas like hydrogen, and you do not see a continuous spectrum but dark lines at very specific wavelengths corresponding to the energies that electrons in hydrogen can absorb. This is not random. It is direct evidence that electrons only react to very specific energies. And what is even more important is, this law does not depend on the type of material or the type of wave. It is a general principle of nature. When you look at everything through this lens, the story starts to become very clear. Electromagnetic waves are not blocked because they are too small or too big, but because the energy of the photons in that wave matches the energy levels of the electrons in the material or not. If it matches, the energy is absorbed and the wave is blocked. If it does not match, the energy is not absorbed and the wave continues through. And this is exactly the key we have been looking for. It explains everything that previously seemed contradictory. It explains why visible light is blocked by walls, why Wi-Fi can go through, and why X-rays can go through the body. Everything comes back to the single principle, the energy match between photon and electron. And when you understand this, you do not just solve one paradox, you completely change the way you look at the physical world, from a world governed by geometry and size to a world governed by energy and very precise quantum rules. At this point, we can apply the energy match principle directly to the most familiar case, visible light when it meets a wall. Let's start with specific numbers so everything becomes clear. Visible light has frequencies from about 4 times 10 minus nq to 7.5 times 10 minus nq hertz. And according to the formula E equals h, if that corresponds to photon energies in the range of about 1.8 to 3.1 electron volts, eV. This is not a random energy range. In fact, it matches very well with the energy levels of electrons in many common materials around you, especially the materials that make up house walls like wood, paint, drywall, and brick. These materials contain complex molecules with electrons bound in diverse chemical structures, and these electrons can transition between energy levels a few electron volts apart, exactly in the energy range of visible light. When a visible light photon enters the wall, it does not hit a solid block in the classical way, but interacts with these electrons. If the energy of the photon matches the gap between two energy levels that the electron can transition to, the electron will absorb that photon almost immediately. The photon disappears. Its energy is transferred to the electron, and then this energy can be dissipated as thermal vibrations or other processes in the material. This happens at extremely high speed and with a huge number of photons, so light has almost no chance of passing through the wall. This is why you do not see light slipping through the wall, even if the wall is only a few centimeters thick. It is not because light is blocked by a solid structure like a sealed metal sheet, but because it is absorbed so efficiently that almost all of its energy is held back. The interesting thing is that this mechanism also explains another familiar phenomenon, the color of objects. When white light, which includes all wavelengths in the visible range, shines on an object, the electrons in the material do not absorb all photons the same way. Instead, they absorb the photons whose energy matches their energy levels and reflect or transmit the remaining photons. For example, a red object absorbs most photons with higher energy corresponding to green and violet light, while reflecting the photons with lower energy corresponding to red. So color is not a fixed property of the object, but the result of selective interaction between light and electrons. This further reinforces the idea that what matters is not the size or shape of the material, but the energy structure of the electrons inside it. Back to the wall. You can see that it does not just absorb part of the light, but absorbs almost the entire visible light range, because the energy levels in its material cover the 1.8 to 3.1 eV range broadly. That makes it an extremely effective filter for visible light, holding back most of the energy and not letting light through. And this is the key point. Light is not blocked because it is too small, or because there are no gaps to pass through, but because its energy is too well matched to the material. It activates the electrons in the wall in a way that Wi-Fi cannot. When you look at this phenomenon from that angle, you begin to see that the wall is not a geometric barrier, but an energy absorption system defined by its quantum structure. This completely changes the way you understand the world around you, because it shows that what you see light being blocked, objects having color, is not the result of shape or size, but the result of very precise energy laws operating at the electron level. And when you have understood this, you have come very close to explaining why some types of electromagnetic waves are blocked, while others pass through the same material. Now let's place next to the story of light a completely opposite case that you use every day. The Wi-Fi signal. When you hold your phone and connect to the internet from a router in another room, that means electromagnetic waves are passing through walls, through doors, even through multiple layers of different materials before reaching your device. This is not magic, and it is not because Wi-Fi finds some gap in the wall. It goes back to exactly the principle we just built. The energy of the photon. Let's look at the specific numbers. Common Wi-Fi operates at frequencies around 2.4 gigahertz or 5 gigahertz. That is 2.4 times 10 mime to 5 times 10 mime hertz. When you apply the formula E equals HF with Hess, 626 times 10 thurs, Y door. Compare this number with visible light, which is in the range of 1.8 to 3.1 eV. That means Wi-Fi photons have energy about 100,000 to 300,000 times lower than visible light. This is a huge difference, not a small detail. And it is precisely this difference that determines its entire behavior when it meets matter. When a Wi-Fi photon enters the wall, it also encounters the same electrons as light does. But this time, the energy it carries is far too small compared to the gaps between the energy levels of the electrons in the material. The electrons in wood, Paint, drywall, or brick do not have any steps spaced only 10^9 EE apart for them to jump to. That means no energy match occurs. And you already know the rule. If there is no match, the electron cannot absorb the photon. There is no such thing as absorbing a part. There is no close enough. The electron simply does not react. And if the electron does not react, the photon is not held back. It continues moving, passing through the material. This is the core reason why Wi-Fi can go through walls. Not because it is bigger, not because it finds a way around, but because it does not have enough energy to be blocked. It is like someone knocking on the door, but not hitting hard enough to make anyone inside react. So the door does not really open. Rather, no significant interaction occurs, and the wave continues through. However, this does not mean Wi-Fi passes through material without being affected at all. In reality, you know very well that the Wi-Fi signal weakens as you move away from the router, or when there are many walls between you and the source. This is because some of the wave's energy is still lost through other mechanisms, such as slight vibrations of electrons, weak absorption, or scattering in the material. But the important point is, there is no strong and complete absorption like with visible light. There is no energy match that causes the entire photon to be held back. Instead, most of the energy continues to transmit through, only gradually diminished by distance and the number of obstacles. This is why you can still pick up Wi-Fi in the next room, but the signal will be weaker than when you stand right next to the router. And this also explains why different Wi-Fi frequencies behave slightly differently. For example, the 2.4 gigahertz signal with a longer wavelength and slightly lower energy usually penetrates walls better than the 5 gigahertz signal, even though both are in the energy range too low to be strongly absorbed. All of this fits the same principle we have built. The behavior of an electromagnetic wave is not determined by its size, but by the energy of its photons and how they interact with electrons in the material. When you look at Wi-Fi this way, you no longer see it as something sneaking through gaps, but as a type of wave that matter almost does not notice, because it does not carry enough energy to trigger any strong reaction from the electrons. If you have clearly seen why light is blocked and Wi-Fi passes through, then the next case will complete the picture: X-rays. This is the example at the other end of the electromagnetic spectrum, where photon energy is much higher than visible light. Let's start with the number. X-rays have frequencies in the range from 10 μe, right, to 10 μe. And when you apply the formula E equals HF, that corresponds to photon energies in the range of hundreds to tens of thousands of electron volts. That is from about 10 squared to 10 eV, usually called keV, compared with visible light, which is only about 1.8 to 3.1 eV. You will see that X-rays have energies hundreds to thousands of times higher. This is an extremely large difference, and it is precisely this difference that determines how X-rays interact with matter. When an X-ray photon enters your body, it does not encounter the same resonance condition as light. Its energy is too high compared to the gaps between the energy levels that electrons and soft tissue can normally absorb. This means it is not easily absorbed through simple energy level transitions like visible light. Instead, the X-ray photon can pass through relatively thin layers of matter like skin and muscle without being completely held back. However, this does not mean it does not interact with matter. At such high energy levels, X-rays can cause other processes, such as ionization. That is, it can supply enough energy to knock electrons out of atoms. But the occurrence of these processes depends heavily on the type of material it passes through. This is the point where bones become especially important. Bones in your body contain heavier elements, especially calcium, with higher atomic numbers than the elements in soft tissue like carbon, hydrogen, and oxygen. Heavier atoms have more electrons and have a stronger ability to interact with X-rays. This increases the probability of absorbing X-ray photons through mechanisms like the photoelectric effect, where the photon is completely absorbed and an electron is ejected from the atom. So when X-rays pass through the body, most of them go through soft tissue, but are absorbed more in the bones. This is exactly why in X-ray images bones show up clearly while soft tissue is fainter. This phenomenon was first discovered in 1895 by Wilhelm Röntgen, when he noticed that an invisible radiation could pass through many materials and create images of bones on a film. It was a revolutionary discovery, and within just a few years, X-rays were put into use in medicine. Today, X-rays are one of the most important diagnostic tools, allowing doctors to see inside the body without surgery. All of this goes back to the same principle we have built from the beginning. The way an electromagnetic wave interacts with matter depends on the energy of the photon and how that energy matches the structure of the electrons in the material. In the case of visible light, the photon energy matches the energy levels of electrons in the wall, leading to strong absorption. In the case of Wi-Fi, the energy is too low and does not match any levels, so it is not absorbed and can pass through. With X-rays, the energy is too high and does not fit the usual transitions of electrons in many materials. So it is not absorbed in the way light is blocked, but instead can pass through matter and is only strongly absorbed in regions with more suitable atomic structure, like bones. So you see a very clear picture, not big or small, but how well the energy matches. At this point, the overall picture has emerged clearly and consistently. Every phenomenon we observe, from Wi-Fi going through walls, light being blocked, to X-rays going through the bodiole, obey the same single principle. That principle has nothing to do with the size of the wave or the geometry of the material, but lies in the energy match between photon and electron. When an electromagnetic wave enters matter, what really happens is not a collision with a solid wall, but a process of interaction between the electromagnetic field of the wave and the electrons in the material. Each photon carries a definite amount of energy according to the formula E equals hf. And electrons can only absorb energy if that value exactly matches the gap between the energy levels they can transition to. This is a discrete law with no gray area. When there is a match, the photon is absorbed. The electron jumps levels, and the energy of the wave is held back in the material. When there is no match, the electron cannot react. The photon continues moving, and the wave passes through. It is this simple but strict law that explains everything that previously seemed contradictory. Visible light, with photon energy in the range of 1.8 to 3.1 eV, matches the energy levels of electrons in common materials like wood, paint, and brick. So it is strongly absorbed and cannot pass through walls. In contrast, Wi-Fi, with photon energy of only about 10 eV, hundreds of thousands of times lower than light, is not enough to excite any level transitions in electrons. So it is not significantly absorbed and can pass through material. Meanwhile, X-rays, with photon energy in the keV range, thousands of times higher than light, do not fit the usual electron level transitions in many materials, allowing them to pass through soft tissue and only be strongly absorbed where there is a more special atomic structure like bones. These three cases are not exception, but three different points on the same spectrum of behavior, all controlled by the same principle about energy. This also clearly shows that explanations based on size or gaps are insufficient and even mistaken. In reality, the distance between atoms in matter, about 10 or more meters, is not the deciding factor in whether a wave passes through or not, because the wave does not sneak through those spaces in a simple geometric sense. Instead, it interacts with the electrons distributed in that space, and the result of that interaction depends entirely on energy. The entire principle can be summarized in one very simple sentence. Whether an electromagnetic wave is blocked or transmitted does not depend on whether it is big or small, but on whether its energy matches the energy structure of the electrons in the material. When the energy matches, the material absorbs and the wave is blocked. When it does not match, the material almost does not notice the existence of the wave, and the wave continues through. This is a completely different view from the initial intuition, but once understood, it not only explains one specific phenomenon, but also opens up a deeper understanding of how energy and matter interact throughout the universe. To make this energy matching principle more intuitive, let's switch to a very familiar image from physics, the phenomenon of resonance, and one of the simplest examples is the tuning fork. Also known as an acoustic fork, imagine you have two identical tuning forks, both tuned to vibrate at the same frequency, for example 440 hertz, which corresponds to the note A in music. You place them a short distance apart. When you strike one, it begins to vibrate and produce sound. The interesting thing is that if the second one is close enough, it will also start vibrating even though you never touched it. This happens because the sound waves in the air carry energy at exactly the natural frequency of the second tuning fork, and the system recognizes that frequency, absorbs the energy, and begins to oscillate. This is resonance. A system only responds strongly when the frequency of the external signal matches its own natural frequency. Now let's change the situation a little. Suppose you have a different tuning fork tuned to 523 Hz, which corresponds to the note C. You strike the 440 Hz tuning fork and the sound waves spread out into space. What happens to the 523 Hz tuning fork? Almost nothing. It does not start vibrating, or it vibrates only very weakly. Why? Because the frequency of the sound waves does not match the natural frequency of the system. The energy is there, but the system cannot absorb it effectively. This is the key point. It is not enough just to have energy. The energy must have the right frequency. And now let's go back to the electrons in a material. These electrons are not free particles, but systems with their own natural frequencies determined by their energy structure. The discrete energy levels we talked about actually correspond to the resonance frequencies that the electrons can respond to. When a photon enters the material, it carries a specific frequency and therefore a specific energy. If this frequency matches one of the frequencies at which the electron can vibrate, or more precisely, transition between energy levels, then the electron will absorb that photon, just like the second tuning fork starts vibrating when it receives the right sound wave. If it does not match, then no significant absorption occurs and the photon continues on its way. Let's start to look back at the whole story in a very intuitive way. Visible light with frequencies around 4 times 10 to 7.5 times 10 the resonance frequencies of electrons in many materials like wood and paint, so it is strongly absorbed. Wi-Fi, with frequencies of only a few gigahertz, that is, hundreds of thousands of times lower, does not match any of the resonance frequencies of the electrons in those materials. So it is not absorbed and can pass right through. X-rays, with extremely high frequencies, interact through different mechanisms but still follow the same principle. The match between frequency and energy determines the degree of interaction. And what is important here, that matter is not a passive wall. It does not just sit there and block everything that tries to pass. It is a dynamic system whose electrons can react or not react depending on the signal they receive. When the signal has the right frequency, the system resonates and absorbs the energy. When the signal has the wrong frequency, the system stays almost silent and lets the energy pass through. This is a completely different way of looking at things from our initial intuition. But it is extremely powerful because it does not just explain one specific phenomenon. It is a general principle that applies to many systems in nature. From sound to light to mechanical and electronic systems, resonance is one of the central concepts that helps us understand how energy is transmitted and absorbed. And in the case of Wi-Fi and light, it is precisely the key to explaining why two seemingly similar types of waves behave completely differently when they encounter the same wall. At this point, you have probably seen the full scientific picture, but let's set aside terms like energy levels, photons, or resonance for a few minutes and try to look at the whole story in a simpler way that is closer to intuition. Imagine you are standing in front of a door that opens only with a key of a very specific shape. If you have exactly that key, the door opens immediately. If you have a key that is almost the same, or even bigger, stronger, or more expensive, but not the right shape, the door still does not open. What matters is not the size of the key, but the fit. And that is exactly how electrons in matter see electromagnetic waves. Each electron is like a lock that only accepts very specific energy keys. When a photon arrives, it is like you are trying to insert a key into that lock. If the photon's energy exactly matches the gap between two energy levels, the electron can transition too. The lock recognizes it and opens the electron, absorbs the photon, and the energy is kept. If it does not match, even by a little, nothing happens. The photon passes through as if the lock did not exist. Now let's go back to the wall. The wall is not a solid, inert block as you might think, but a huge collection of energy locks. the electrons, each tuned to respond to certain energies. Visible light carries photons with energies in the range of 1.8 to 3.1 eV, and it just so happens that this is exactly the range of energies that many electrons in materials like wood, paint, and brick can respond to. So when light hits the wall, it is like having billions of perfectly fitting keys for billions of locks. The electrons open the doors, absorb the energy, and the light disappears from the other side. Nothing gets through, not because it is geometrically blocked, but because the energy has been almost entirely captured. In contrast, Wi-Fi carries photons with extremely low energy. Only about 10 is a minor benefit. Imagine you are trying to open the same lock with a key that is too small, too weak, not even enough to reach the mechanism inside. You can try as many times as you want, but the lock will not respond. That is exactly what happens with the electrons when they encounter Wi-Fi. The energy is too low and does not match any of the steps the electrons can climb. Therefore, there is no absorption, no reaction, and the wave passes through as if nothing were in the way. This does not mean matter disappears. It means matter simply does not care about that type of energy. And with X-rays, you have a different situation. The photons carry very high energy, thousands of eV, like a key that is too strong. It may not fit the lock in the usual way, but it is strong enough to break the structure and knock electrons out of atoms. So it is not absorbed the way light is blocked. Instead, it passes through many materials and is only stopped in places with more suitable structures, like bones. When you look back at the whole story this way, everything becomes very clear and consistent. There is no contradiction at all. There is nothing strange about Wi-Fi going through walls while light does not. Everything follows the same very simple principle. The energy has to match, not size, not shape, not gaps. That is why the initial explanation many people give that long waves go through and short waves are blocked is an oversimplification that leads to misunderstanding. In reality, visible light has a much longer wavelength than the distance between atoms, yet is still blocked, while X-rays have shorter wavelengths and pass through. That shows that size is not the deciding factor. What decides is whether the energy of the wave speaks the right language to the electrons. And once you start seeing the world this way, you will notice that many other phenomena around you also work according to the same principle. Matter is not a static wall, but a system that responds selectively to energy. It listens to certain frequencies and ignores others. And in this story, visible light happens to fall within the range that the wall listens to, while Wi-Fi does not. And that is the whole secret. A very interesting example that reinforces this entire way of looking at things is glass and ultraviolet light. Because here you will see that the same material can be both transparent and completely blocking, depending only on the energy of the wave. Let's start with the numbers. Ultraviolet light, or UV, lies just above visible light in the electromagnetic spectrum with higher frequencies and therefore greater energy. If visible light lies in the range of 1.8 to 3.1 eV, then UV light typically lies in the range of about 3 to 10 electron volts and can even be higher depending on the type. This means that by simply increasing the frequency slightly beyond the violet region, you have stepped into an entirely different energy region in terms of interaction with matter. Now let's go back to glass, specifically silica glass, the type of material used in most windows. You already know that glass lets visible light through very well, transmitting about 90% of the light under ideal conditions. That means the electrons in silica do not absorb photons with energies from 1.8 to 3.1 eV very strongly. In the way we just built, the energy locks in glass are not tuned to respond to that energy range, so the light passes through with almost none of it being held back. But when you switch to UV light, the situation changes completely. UV photons carry energies from about 3 to 10 eV, and this energy range begins to match the gaps between the energy levels of electrons in silica. That means when UV light hits the glass, the electrons in the material can absorb this energy effectively. The photons are held back, the energy is transferred into the material, and the UV light cannot pass through. This is not a small change, but a very clear transition. The same material is almost transparent to visible light, but becomes an effective barrier to UV light. This is direct evidence that transparency or opacity is not a fixed property of the material, but depends entirely on the energy of the wave interacting with it. A very familiar example from everyday life will help you feel this more clearly. When you stand inside a house behind a glass window, sunlight still shines in and you can see everything clearly, but you do not get sunburned the way you do when standing outside. Why? Because most of the UV rays from the sun have been absorbed by the glass before they reach your skin. Visible light passes through, bringing images and brightness, but the higher energy portion that can damage skin is blocked. This is not because the glass is thicker or denser for UV. It is because the electrons in the glass can absorb the energy of UV photons but do not absorb visible light. This is the same principle we have seen from the beginning. Energy matching determines everything. If the photon's energy lies in the region where the electrons can respond, the material absorbs and blocks the wave. If not, the wave passes through. And the interesting thing is that you can change this behavior by changing the material. For example, some special types of glass, such as pure quartz glass, have a different energy structure and can let more UV light through than ordinary glass. That shows there is no fixed rule like glass always blocks UV or glass is always transparent. Everything depends on the specific energy structure of the material. When you look back at the whole story with this example, you will see that it not only reinforces the principle we have built, but also expands it. A material is not transparent or opaque in an absolute sense. It is only transparent to certain energy ranges and opaque to others. And this means that the reality you experience, what you see and what you do not see, depends on how the electrons and matter interact with specific energy ranges. Visible light is only a very small part of the electromagnetic spectrum, and you only see what matter allows that light to pass through or reflect. Things outside that range, like UV light, can be completely blocked without you even realizing it. And that is a beautiful demonstration of our central idea. The world is not defined by shape or size, but by subtle energy rules operating at the microscopic level. From all the examples we have just gone through, an almost inescapable conclusion begins to emerge clearly. What determines how an electromagnetic wave behaves is not the material itself, in the sense of solid or empty, but the frequency of that wave, or in other words, the energy of the photon it carries. When you change the frequency, you change the energy. And when you change the energy, you completely change the way the electrons in the material can respond. This leads to a very important consequence. The same material can be transparent, opaque, or reflective, all depending on the frequency of the electromagnetic wave entering it. Let's go back to the glass example we just talked about. With visible light at frequencies around 4 times 10 mu, Debunking to 7.5 times 10 mu. Debunking. Glass is almost transparent because the electrons in silica do not have matching energy levels to absorb strongly in that range. But if you increase the frequency just a little and step into the UV region with energies around 3 to 10 eV, you activate a series of energy transitions in the electrons, and immediately the glass becomes opaque to that type of wave. Nothing changes geometrically. Nothing changes in the physical structure of the glass sheet. Only the frequency of the wave changes, and the entire behavior changes with it. The same thing happens with many other material. Water, for instance, is transparent to visible light, but absorbs strongly in the infrared region, where photons have energy suitable for exciting vibrations of water molecules. That is why water can heat up when it absorbs infrared radiation. Metals, from another angle, reflect visible light strongly, because the free electrons in the metal can respond to that frequency in a way that creates a reflected wave. But with other frequencies, their behavior also changes. When you look at the entire electromagnetic spectrum, from radio waves, microwaves, infrared, visible light, ultraviolet, X-rays to gamma rays, you will see that there is no hard boundary between the types of waves. They're all electromagnetic waves. They all obey the same Maxwell's equations, and they all travel at the same speed of light. The only difference is frequency, and that difference alone creates the entire diversity in how they interact with matter. This is an extremely powerful idea because it completely reverses the way you usually think about the world. Instead of asking, what is this material in a static sense, you have to ask, how does this material respond to each different frequency? A wall is not simply blocking waves or not blocking waves. It is a system whose response depends on frequency. It blocks strongly in the visible light range, is almost transparent in the radio wave range, and may respond differently in higher frequency ranges. This also explains why you can use different types of waves to see through matter in different ways. Radio waves and microwaves are used in communications because they can pass through many materials without being strongly absorbed. X-rays are used in medicine because they can pass through soft tissue but are absorbed in bone. And visible light, which your eyes perceive, is only a very narrow band where the matter around you happens to interact in a way that creates images. When you understand this, you begin to see that the concept of transparent or opaque is not an absolute property of a material. An object can be completely transparent to one type of wave and completely non-transparent to another. Glass is transparent to your eyes, but to a creature that can see UV light, it might look like a wall. And to a Wi-Fi transmitting system, the wall in your house is not an absolute barrier, but only an environment that attenuates the signal. This leads to a deeper realization. The reality you experience is only a very small part of what actually exists, and it is shaped by how specific frequencies of electromagnetic waves interact with matter and with your senses. Frequency is not just a technical detail. It is the factor that determines everything in this story. It determines whether energy is absorbed or not, whether the wave is blocked or passes through, and ultimately how you see and understand the world around you. Once you have accepted that frequency determines how electromagnetic waves interact with matter, a natural question arises. Do the things we see really reflect the world as it actually is, or are they only a very narrow slice selected by our senses? Humans can only see an extremely small range of the electromagnetic spectrum, from about 400 to 700 nanometers, corresponding to photon energies from about 1.8 to 3.1 eV. That is visible light. But the electromagnetic spectrum stretches from radio waves with wavelengths of many meters to gamma rays with wavelengths smaller than the size of atomic nuclei. That means most of reality in the form of electromagnetic waves is invisible to you. And this is where biology enters the story. Other creatures are not necessarily limited to the same frequency range as humans. For example, bees can see ultraviolet, UV light, with wavelengths shorter than violet light that the human eye cannot perceive. To them, the world looks very different. Flowers that you see with simple colors appear with complex patterns in the UV region, like landing strips, guiding bees to the nectar center. These patterns are completely invisible to you, but are important signals in the ecosystem. This is not a small detail, but strong evidence that the reality each species experiences depends directly on how its sensory system interacts with different frequency ranges of electromagnetic waves. The human eye evolved to respond to the visible light range, because that is the energy range suited to the environment on Earth, and the sunlight from the sun. But there is nothing special about this range beyond the fact that it fits our biology. If your eyes were sensitive to UV, you would see a different world. If you could see infrared, you would see heat instead of colors. If you could sense radio waves, you would see Wi-Fi and television signals spreading through the space around you. This leads to a very profound conclusion. Every species lives in its own version of reality, defined by how its body interacts with energy. Reality is not a single picture, but a set of possibilities, and each creature only accesses a part of it. When you look at a wall and see it blocking light, that is because your eyes only perceive the energy range that the wall absorbs strongly. But to a Wi-Fi transmitting system, that wall is not a complete barrier, because in that frequency range the electrons in the material do not respond strongly. And to a creature that can see UV, a glass pane that is transparent to you might look like an opaque wall. All of this comes back to the same principle we have built. The way electromagnetic waves interact with matter depends on energy, and the way you perceive the world depends on the energy ranges you can sense. This means that the world you see is not the entire world, but only the intersection between the electromagnetic spectrum and your ability to perceive it. And when you realize that, the story of Wi-Fi and light is no longer just a pure physics issue, but becomes a door opening to a larger question. How much of reality are we really seeing? and how much more is existing right around us that we are completely unaware of simply because it lies outside the frequency range our bodies can perceive. From that perspective, something that seemed obvious begins to waver. There is no such thing as a completely transparent object, and there is no such thing as a completely blocking object. Concepts like transparent or opaque only make sense when tied to a specific energy range you are considering. A glass pane lets visible light through almost easily, but blocks most ultraviolet light. A wall prevents your eyes from seeing through, but lets Wi-Fi signals pass. Your body can block light but is almost transparent to X-rays at many energy levels. This is not an exception or something strange, but the direct manifestation of a deeper principle. The properties of an object are not fixed features, but the result of the relationship between matter and the energy interacting with it. When you say an object is transparent, that really means that in the energy range you're observing, the electrons in that material do not absorb photons strongly, so the energy can pass through. When you say an object blocks, that means in that energy range the electrons absorb or reflect strongly, so the energy cannot continue to propagate. None of these definitions exist independently of energy. This forces us to change the way we understand the physical world. Instead of viewing matter as blocks with fixed properties, we need to see it as dynamic interacting systems where electrons respond to energy according to very precise and discrete rules. Each material, in that sense, is like an energy filter that lets some frequencies through, holds back others, and reflects the rest. And this filter is not determined by the shape or size of the object, but by the internal energy structure. That is, how the electrons are arranged and the energy levels they can transition to. When you change the frequency of the electromagnetic wave, that is, change the energy of the photon, you are not just changing a technical parameter. You are completely changing the way the material responds. An object can switch from transparent to opaque simply by changing the frequency of the wave shining on it without changing any geometric properties. This shows that the concept of obstacle we commonly use in daily life is really just an oversimplification. A wall is not an absolute barrier, but a system that responds selectively to energy. It blocks light because light carries energy suited to being absorbed, but it does not block Wi-Fi because the energy of Wi-Fi is not enough to excite the electrons in the same way. If you change the type of wave, the role of the wall also changes. This opens up a broader view. The world is not made up of objects with fixed properties, but of continuous relationships between energy and matter. What you observe depends not only on the object itself, but also on how you interact with it, on the type of energy you use to probe it. The light your eyes receive is only a very small part of the electromagnetic spectrum, and therefore the world you see is only a very narrow slice of reality. When you change the way you observe using X-rays, radio waves, infrared, or ultraviolet, you are not just looking at the same world differently, you are accessing completely different aspects of it, things the naked eye cannot perceive. This leads to a philosophical realization. Reality is not a fixed picture that exists independently of the observer, but a set of possibilities, manifested differently depending on how energy and matter interact. An object can be both transparent and opaque at the same time as long as you change the frequency of the wave you use to observe it. This is not a paradox, but a natural consequence of the quantum world, where everything is defined not only by itself but by the way it interacts. And when you look back at the original question about Wi-Fi and light, you will see that it is no longer something strange, but only a very specific example of a much deeper principle in this universe. Nothing is defined absolutely. Everything only has meaning in relation to the energy it interacts with. Now let's return to the exact question that started this whole journey. Why can Wi-Fi pass through walls while light cannot? At first it seemed like a paradox, something that contradicts our very basic intuition about the world. But as we went through each layer of the problem, from atomic structure and discrete energy levels to the nature of the photon and energy matching, the answer gradually emerged not as a mystery, but as an inevitable consequence of the way nature operates. Wi-Fi does not pass through walls because it is cleverer, and light is not blocked because it is too small. It is all simply a matter of energy. One type of wave carries energy suited to being absorbed, the other does not. But what is more important than that specific answer is the lesson it brings. This whole story is a reminder that our intuition, which is shaped by everyday experience at the human scale, is not always a reliable guide when we step into the microscopic world. What seems obvious, like the idea that matter is solid, that big waves pass through while small waves are blocked, can turn out to be completely wrong when faced with experimental data. And instead, the world operates according to much more subtle rules, where energy, frequency, and quantum structure play the decisive role. This also opens up a broader perspective on the reality we live in. What you see, what you consider obvious, is really only a very small part of a much larger picture around you right now. Countless electromagnetic waves with different frequencies are propagating from Wi-Fi signals and radio waves to infrared and ultraviolet radiation. But you do not notice them simply because they lie outside your ability to perceive them. And even the most familiar objects, like a wall or a pane of glass, do not have the fixed properties you once thought. They are not always blocking or always transparent, but only respond in specific ways to each type of energy. When you change the way you look, you change the way you see. And that is perhaps the most interesting thing in this entire story. Not that we have explained a specific phenomenon, but that we had to change the way we ask questions in order to do so. Science does not just provide answers, it also forces us to abandon old assumptions and learn to see the world in new ways. So the next time you walk into a room and see light stopping at the wall while Wi-Fi still silently passes through it, remember that you are witnessing not a paradox, but a subtle manifestation of the deepest laws of nature. And perhaps the more interesting question is not why these two types of waves behave differently, but how many other things in the world around you are operating according to principles you have never noticed, simply because you have never asked the right question. If you find that this way of looking at things makes the world more interesting, please subscribe to the channel so you do not miss questions like this. Simple, but change everything. See you in the next video, where we continue to explore the secrets hidden behind the most familiar things.